Let's work a sample problem in plane waves. What's an example of a problem that I can ask you about plane waves in? Let's see if we remember from our lectures and our review in our undergraduate electromagnetics how to solve a basic plane wave problem. So we'll start that way today. Okay, so let me start with the problem statement. I brought a nice sample problem to work. A UHF satellite is transmitting a circularly polarized wave to a boat. On the surface of a calm lake. In the immediate area around the boat, the radio waves behave like a plane wave. This is actually very typical. This is one of the reasons why we study plane waves. If you understand how to parse a plane wave, you understand like 80% of electromagnetism, whether you realize it or not. Because everything is just kind of a variation of this construct. A source, for example, all of our antennas, if you step back and look at them, behave as point sources. And if you travel far enough away from that antenna and just look at a little local area, that wave that the point source emanates looks pretty much like a plane wave. And this is true for satellite communications as well. So, we transmit this wave to a boat, and the equation for electric field, E field, for this wave as it propagates around the boat is given by E vector. And you'll recall in this class, I put a squiggle on it because we'll be using phasors from here on out. All of our field quantities are time harmonic. Assume sinusoidal excitation at some time at t equals to minus infinity that has reached a steady state and persists to t plus infinity. And that's a wonderful way to study both electromagnetics and circuits in RF for satellite communications. Because at some point, everything kind of looks like a sinusoidal wave. We might change the amplitude a little bit, modulate the frequency a little bit. But a pure sine wave is a great way to estimate how our signal is going to behave in a system. Same with the E field. We've got a time harmonic system. Since we know it's a sinusoid and we've converted it to the phase domain, all this squiggle means, the phasor domain, the squiggle means that we're tracking amplitude and phase. We're not going to record frequency and the actual cosine 2 pi ft time dependence plus some sort of phase, because that's going to be same. That's going to be along for the ride for this entire problem. And so as electrical engineers, we convert to the phasor domain. We just track amplitude and phase. And that simplifies our life considerably. Now, this E field is going to be equal to 100. I'm going to do a little math here, a little vector math. X hat plus Z hat. These are unit vectors. Of course, this is an E field. So not only does it have a magnitude, but it's got a direction. This is the force that a little test charge would get pushed in. The direction and the acceleration, effectively, or the force. Times exp minus 60 x hat minus z hat dotted into our vector. And this has units of microvolts per meter. Now, just as a point of clarity, we took out the time dependence, but there's still a 3D space dependence. So this R observation vector, we call this the point of observation in 3 dimensions. And it's just a shorthand way of writing your x, y, and z dependence in three dimensions. So instead of writing E as a function of x and y and z, three scalar variables, you just put an R vector in there and greatly simplify your notation. So here's our given. We've got this wave. It's washing over the Earth. In this case, we are going to be using, okay, let me draw my little C with a boat in it. It'll be a little steamboat. And we'll be using this type of coordinate system. We'll put the origin here. X is here. Z should be straight up in the air. Z hat. And if this is a right-handed coordinate system, then Y should go into the board. We'll draw these as unit vectors. These are where the unit vectors point. X, Y into the board, Z straight up. Okay, now we're going to figure out a couple things from this electromagnetic waves. The first thing we need to know, and this is very important for satellite communications, if we're given this E field, where do we point a directional antenna to receive the signal with maximum signal strength? So there's three pieces of information that we'll work on in turn. We want what is the azimuth and elevation angle of arrival, often abbreviated AOA in RF. The other thing, another piece of information that we're going to want is what is the corresponding magnetic field expression? In electromagnetics, where there's E, there's always H. Where there's smoke, where there's fire. In order to satisfy Maxwell's equations, first of all, as you saw in the review videos, that satisfies Maxwell's equations, that plane wave expression there. But in order to do so, there must also be an accompanying H field expression. So it turns out if we can figure out what one looks like, we can figure out what the other one looks like as well. In order to satisfy Maxwell's equations, H has to take a particular form if E takes that particular form. And we'll learn how to do that in this class too, or review, as it is the case. Another basic piece of information we want, what is the frequency of this radio wave? How do we span the gap between our physical expressions that we learn in physics class to some fundamental, useful engineering constructs? Like, what is the frequency? And then D, here's a good one. This will introduce us at least to link budgets. Estimate the power that a dish antenna would collect if it had 2 square meters of aperture that was optimally pointed. Oh, that's a good one. That's a really good one. Okay, so on this board, on this next blank board over here, I'm going to put down the generic formula that all plane waves take if they satisfy Maxwell's equations in a simple medium. What is a simple medium from the review lectures? This is a good test to see if people actually reviewed this material. What are the attributes of the simple medium? No. Don't all raise your hand at once. There, folks. Go.
Isotropic.
Isotropic. That's a great word. It means that it's the same in all directions. The E field is basically the times the permittivity is equal to the electric flux density. It doesn't matter which way you point the E field. There it is again, the aerospace engineers shaming the double E students. Would you care to venture any other attributes?
Homogeneous.
Homogeneous. The medium does not vary as a function of space. If it has epsilon r and mu r over here, it has the same electrical characteristics over here and down here and there. Homogeneous. I like how you pronounce that, homogeneous. For some reason, we pronounce it homogeneous in electromagnetics. For many other things, like when it comes to milk, it's homogeneous. But it's the same word. Isn't that weird? Isn't that weird? Homogeneous, homogeneous. Difference between milk engineering and electromagnetics engineering. You're on a roll. Would you care to offer up any other attributes of a simple medium? No, that's okay. You're still my favorite student right now. You can't ruin it.
External charges? No other charges?
Yeah, source free. So simple media is isotropic, homogeneous. It's also linear. And you were about to say that, right? It's like linear. Oh, yeah, I was about to say that. Oh, no, sorry. Didn't get to you in time. Nice try. And that's a simple medium. And then when you add the set forth attribute, source free, that's when you get a simple plane wave propagating. And air and space look almost the same, at least to an engineering point of view. There's a couple of slight differences. We'll cover them when we get into more deeper propagation topics in satellite engineering. We're just kind of building the fundamentals now. We'll get to link budgets, and then we'll start adding terms to our link budgets that satellite engineers care about. They care about things that other RF engineers don't care about. So, for example, what are the things, does anybody work in like mobile communications, like down-to-earth communications? Anyone researching in that or in a former life professionally worked in it, studying that type of wireless communications in your laboratories? No? None? Unusual. Well, what does a cellular engineer care about? They care about things like interference, small-scale fading, multipath, frequency selectivity, mobile devices, detuning of antennas in the RF link. Those are things that, by and large, except for maybe a few specialty cases, we don't care about those things in satellite engineering. We care about things like propagation through a charged medium in the ionosphere, propagation losses through atmospheric effects at very high frequencies, rain attenuation. And those are things that mobile people don't really care about because they work at lower frequencies and they don't have to worry about that type of stuff. But these are the basic building blocks. And the thing is, the basic building blocks are good to get to either of those fields of knowledge and propagation once you've kind of mastered these basic constructs. So, okay. What is a plane wave supposed to look like? This is the general form of a plane wave, a uniform plane wave to be exact. There are also non-uniform plane waves that satisfy Maxwell's equations, but those are less interesting. Those tend to occur very close to sources, and in homogeneous media, we don't care about that. We just want to learn about plane waves. And it turns out the uniform plane wave describes, or a combination thereof, describes most of propagation in free space. So the general form of the uniform plane wave takes this characteristic equation. Phasor E field has an amplitude, and I'll write the variables and their units and their names underneath here. It has a polarization. My unit vector E hat, you'll get used to this terminology in my class when I draw on the board. A little caret on top of a letter denotes that this is a unit vector, that when you dot it with its self-complex conjugate, you get 1. A lot of textbooks, they use like bold. I can't draw bold on the board, so I use that really old school notation, which is a hat. a little hat. And then just a little arrow if it's a vector, but not necessarily a unit vector. So amplitude, polarization, and then there's a phase term, exp to the minus j, a value called wave number, which I'll describe in a second, times the direction of propagation, which is a little k hat, dotted into your point of observation vector, your x, y, and z. And you can actually add an arbitrary phase to that as well, and you'll get something that satisfies Maxwell's equations. But I won't bother with that yet. And if the E form field takes that form, then the H field must take this form. It is equal in amplitude to E naught divided by something called the intrinsic impedance mu. I'll write about that in a second. It also has a polarization, A hat, and then it has the exact same phase propagating term. Okay. E naught, we said, is the amplitude, really is the peak amplitude of the E field. Units of volts per meter. The intrinsic impedance, eta, has units of ohms, and it is actually equal to the square root of mu over epsilon, the fundamental permeability and permittivity of the medium, just so that you have them in your notes. If this is free space, mu is mu naught, that's 4 pi times 10 to the negative 7 henries per meter, and epsilon naught is 8.85 times 10 to the negative 12 farads per meter. You divide it, you get square root of henries over farads, and that gives you ohms. And that's not the ohms of a resistor that absorbs power, but it's a transport impedance. That is the natural ratio of E to H that this medium carries waves. So if you study transmission lines, you know transmission lines also have an intrinsic impedance like this. It's a ratio of voltage to current that structure naturally carries energy with. Okay. So that's the intrinsic impedance. Let's see, what else do we have? E. This is a polarization of the E field. It is unitless. It is ironic that all unit vectors are actually unitless, technically. Or a paradox or something like that. When people talk about the polarization of the wave, this is the vector that they're talking about. The way we've written the equation up here, H, this is the polarization of the magnetic field, the H field. However, even though this has a different polarization than the E field, when we just talk about generic polarization, usually the E field is what we're referring to. So if somebody just says polarization, we're really talking about E. They're not usually talking about H. K is the direction of propagation of the wave. And it turns out that if this satisfies Maxwell's equations, these three are actually interrelated by the following relationship. K is equal to E cross H complex conjugate. So if I have an E field and an H field, those cross together to produce a K, a direction of propagation. And the unit vectors are all mutually orthogonal to one another. That's actually what this relationship means. They are mutually orthogonal. So I'm sure you probably learned to do the right-hand rule on your physics tests as an undergraduate, right? The instructor would give you like an E and an H, and you had to figure out which direction it was propagating. I always felt a little awkward because it looks kind of corny, and it looks like maybe you're making an obscene gesture to your classmates On my tests, it's okay. We're all friends. We all know what you're doing. So I want to see this if you need to tackle one of these problems, okay? K equals to E cross H. Let's see, what else do we have up here? Anything else we didn't define? Ooh, this is an important one. The wave number. This has units of radians per meter and is actually equal to 2 pi over lambda. The wavelength of radiation. Lambda, of course, when you multiply by frequency, that is equal to velocity of propagation, as meters per second. And that, of course, is equal to 1 over the square root of mu epsilon. So this is our cheat sheet for solving this problem. And we're going to go and we're going to start at A. What is the azimuth and elevation angle of arrival for this particular plane wave? Okay. I'm going to bring it down. Now, let me go ahead and parse this in terms of the plane wave information that I've just provided. I'm going to do a little bit of adjusting, because this is just pure mathematical convenience, the way I've expressed the original E field in this problem. I need to massage this so that it's actually in the form of something useful. And to do that, I'm going to first normalize all these vectors so that they're unit vectors. That way, I can at least kind of make a correspondence to what the physical quantities are in my plane wave equation. So, for example, this is technically not a unit vector. You remember how to normalize unit vectors, right? You take the magnitude of the unit vector and then factor it out. In this case, I got a 1 on the x, a 1 on the z, using the Pythagorean theorem. Square root of 1 squared plus 1 squared is square root of 2. That means this is the length 2 square root of 2 vector. I'll pull that out. And now I should have a true unit vector. And then likewise, I need a unit vector in this phase propagating term. And again, I have the same square root of 2 that I can factor out. Dotted into R. And so now I can draw a correspondence. This is clearly my E naught. This is my E hat. This is my wave number. This K hat describes the direction of propagation, as long as there's a minus sign in front of it. So let's figure out where these things point. My first question was, where is the direction of propagation? So remember, we were on the boat. And let's see. We have an X, Y, Z. My K hat has a positive X component to it, so it's got a component there, and a negative Z component. And so the resultant would point in that direction. This is the direction that the plane wave, the uniform plane wave, is pointed. Now, how do I describe that in terms of angle and azimuth and elevation? Well, it depends on the convention. Here's where, because I didn't specify it in the problem, if you specify your convention and are consistent with it, it doesn't matter what convention you use. I don't care. I will give you full credit for this problem. So, for example, you could use the electromagnetics convention, which says that elevation is measured from the z-axis. And in this case, we get 45 degrees. And you could use the look angle convention that we developed when we were talking about pointing dishes and directional antennas to satellites, where you measure instead elevation from the horizon. For this example, and only this example, they're exactly the same angle, right? If I measure it that way, I get 45 degrees. Now, azimuth if I want to point into the direction of arrival, remember, this is pointing along the x-axis. But here again is sort of a kind of a semantical point, right? If I have an angle of arrival, I want to know where is the wave coming from. So technically, this vector points in negative 45 degrees, but it's coming at positive 45. Likewise, if I define the x-axis as azimuth 0 degrees, the wave is actually coming from 180 degrees, right? Or if you define positive y as north, and you want to use the cartographer's convention, it's coming from 270 degrees. Just specify on your answer what convention you're using, and I'll adapt accordingly. I'll figure it out from what you're telling me. But this is the semantic point that I wanted to make. When you specify an angle of arrival in radio wave propagation, it's always opposite the direction of travel, the direction of the k-hat vector, right? And that makes sense, right? It's like if you were ready to, let's say you were standing next to your friend up on 10th Street. You're getting ready to cross. And your friend starts to take a step into the street. And it turns out there's a big semi coming this way. This is the k vector of the semi. You don't tell your friend, look! That would be a really lousy thing to do. You reverse the director and the direction, the k vector, and say, there's the angle of arrival you should be paying attention to. And he would take his directional optical antennas, and he would look, and hopefully would avert a catastrophe. Okay. Like 50% of any field is always semantics, right? So just be aware that when somebody asks you the angle of arrival, you mathematically parse the direction of propagation and then reverse it for reporting purposes. Okay. So we can say the angle of arrival, we've successfully answered question A. Angle of arrival is 45 degrees elevation and say 270 degrees azimuth if north corresponds to the y-axis, looking down on the map. If I would have accepted, if you said with respect to x hat, I would have accepted the answer 180 degrees as well. That's perfectly the same thing. Okay, any questions so far about that part of the problem? Perfect understanding? You all 7th level wave masters yet? You will if you can answer the next question, which is what is the corresponding magnetic field? So we know what the amplitude of the E field is. It is 100 times the square root of 2. I have to divide by the intrinsic impedance of the medium. What is the intrinsic impedance of the medium of free space? Square root of, yeah.
177 ohms?
Oh, that's a great one. I love a man that memorizes his physical constants. Excellent. Well done. 377 ohms, the magic number. And it doesn't matter whether you're in air or you're in vacuous free space around a satellite. It's the same number. The epsilon r of air is not magnetic, so you get virtually no mu sub r, or permeability different from free space. For epsilon, there's a slight difference. For most applications, you just ignore it and use epsilon naught. You might be a few meters off if you don't use that for GPS or something like that, but for the most part. And so square root of mu naught over epsilon naught is 377 ohms. Now, I know what my K is, and I know that E crossed into H is equal to K hat. E crossed into H is equal to K hat. So check this out. I'm going to do a little switcheroo. If I know E, I know H, I know K. My K was kind of like going down like this. So here. E, H, K. That's my wave. But in this problem, I know E, that's my thumb. I know K, that's swear finger. I don't know H, so I have to do this. If I reverse it, I find that K cross into E should be equal to H. Complex conjugate. In most problems, we don't worry about the complex conjugate. Most of our unit vectors are purely real or well-defined. But to work with complex unit vectors, you actually need that complex conjugate to solve Maxwell's equations. And actually, it was important in this particular example because you'll notice that there's slanted polarization. Okay, so let's do this. E is x plus nothing on the y, 1 over square root of 2 on the x, plus nothing on the y, plus 1 over the square root of 2 on the z. And k, actually, let me write this a little bit. Do you remember how to take determinants? You'd put x hat, y hat, and z hat on the first row, and you take your cross product by populating the first thing on the second row. That's 1 over the square root of 2, nothing on the y, and then minus 1 over the square root of 2. And then my third thing here is 1 over the square root of 2, 0, positive 1 over the square root of 2. And you take the determinant, and that's basically the cross product that we come up with. What is the determinant in this case? X. I multiply these components together. I do x times 0 times 1 over square root of 2. Y times this times this. So I get y half with a minus sign on it. Z times 1 over square root of 2 times 0, that's 0. And I got to subtract the upper diagonals, right? I got to this times 0 times z, 0 times this times x. The only non-zero upper diagonal is going to be minus 1 over the square root of 2 squared y. And you get minus y hat as your h. As your h hat. And you probably could have done that by inspection, right? You say, well, go back to the diagram here. My k hat is pointing this way. You said my e hat is pointing this way. Let's see. K cross e should make an h that's coming out of the board. Well, that's negative y hat, the way that we've defined it. So the math and the geometrical common sense may work together and are consistent with one another. Does everybody see how I got that? This bring back bad memories of cross products in your vector calculus class, right? Vector geometry class. It's all just a bookkeeping scheme to make sure that your math works out right and you don't make anything contradictory happen. Well, we've done the hard part. It turns out that the rest of the H field looks exactly like the E field. And so if we wanted to come out with the actual expression by simplifying it, our final answer for part B, what does the corresponding magnetic field look like? I type it into my magic professor calculator, where all the answers are calculated ahead of time. It looks something like this. And that's in nanoamps per meter. Units of amps per meter, or nanoamps per meter. That's the units that we put magnetic field in. Okay. Now, the next question, see, what's the frequency? Well, luckily, we've done all the hard work here. We've already established that k, the wave number, is 60 times the square root of 2. That was the thing that we factored out of the unit vector, the residual stuff left over. And, of course, that means that 2 pi over lambda is equal to 60 times the square root of 2. We know that lambda is equal to velocity of propagation divided by frequency, which means I can put velocity of propagation times frequency up here. Velocity of propagation is just 1 over the square root of mu epsilon. So I can write this actually as 2 pi f square root of mu epsilon. This is free space, so I'm going to put mu naught and epsilon naught. Solving for frequency, frequency is equal to 60 times the square root of 2 pi, the square root of 4 pi times 10 to the negative 7 henries per meter times 8.85 times 10 to the negative 12 farads per meter. I put this into the magic professor calculator where everything is calculated ahead of time, and my final answer is 4.1 times 10 to the 9th hertz, 1 over seconds. 4.1 gigahertz. Right? 4.1 gigahertz. Nice microwave frequency. And we pulled that out, that physics, out of the mathematics of the plane wave. Now, this might be a good time to mention, I don't know if I've done this before. You'll notice that I used the term gigahertz, not this gigahertz stuff that you guys are all probably doing, right? Has anybody wondered why I'm doing that and been too embarrassed to ask? So you'll notice in the dictionary that both pronunciations are accepted. The term prefix giga comes from the Latin gigos. Every instance of that Latin word in English is a j sound. Giant. Gigantic. Giga. Right? So I maintain that that's the proper way to pronounce it. And I'm leading this lost cause in life to change everybody's pronunciation of that word. Just for etymological consistency. I maintain that Hollywood in Back to the Future got it right. And then they blew all their credibility on flux capacitors. But that's a different story altogether. But it really was 1.21 gigawatts. In fact, I heard a Verizon commercial on the radio the other day, and it was grating on my spine. They said, you can buy like 10 gigantic gigs. I was like, oh, stop it. You're torturing me. You're torturing me. Now, of course, there's always a little smart aleck student in the class that said, oh, that's very interesting, Professor Durgin. And in fact, my name is pronounced with a hard G. I was like, no, I'm being consistent. I'm not arguing for consistency in the English language, which is the one true lost cause in this world. Rather, my name comes from a Germanic root. It's actually, it's a Scottish word. I think it means dragon or something like that in Old English. I don't know. But it's always been a hard G. So, anyway, in case you were wondering, that's why I talk the way I do. Now, we have one more thing. It was a great question to ask. Now that we understand this plane wave and been able to parse it, does anyone have any questions before we do the really cool calculation? Okay, what was the really cool calculation? This was part D, which said that we had a dish antenna. and we had the wherewithal to compute our look angle at 45 degrees of elevation and 270 degrees azimuth. We pointed the dish antenna. The dish has 2 meters squared of physical aperture. How much power, and this is an upper limit, this is ideally with no losses, perfectly grabbing power out of a plane wave, can we pull out of this radio wave? We know it's E field. We know it's H field. We know this collecting aperture that we can gather energy over. There's one thing that we need to do before we get this answer. We need to calculate something using E and H. What is it? What is the quantity that we need, the physical quantity, the name in electromagnetics, before we can make this calculation? The gain. Well, no, not yet. Not yet. This is... You're reading ahead of the lecture, actually. We're going to get to gain next week of an antenna. Maybe even Thursday. But actually, you have enough information to answer this question without knowing what the antenna gain is, because I gave you something that's related, which is the aperture size. Power density. What is that called in electromagnetics? Pointing vector. Excellent. He is now my new favorite student. The Poynting vector, named after a dude named Poynting, which is why it's funny. All the vectors point. There's no reason. It's redundant to say Pointing vector. The Poynting vector is defined, and this is average, time average, because remember, we're dealing with sinusoidal quantities. And so the peak energy or peak power density is going to be different than the time average quantity. Because we're dealing with pure sinusoids, it's actually very easy. The peak is given by E cross H, complex conjugate, and you put a 1/2 in front of that to get the average. This is a vector. It tells you the direction of net energy flow. And the magnitude tells you that the quantity, the amplitude of that flow in watts per meter squared. How do I know it's watts per meter squared? Well, remember, E field is volts per meter. H field is amps per meter. Put them together, and I have a quantity, S, my Poynting vector, that has units of volt amps per meter squared. Volt amps, of course, anybody who's taken an elementary circuits class knows that to be watts. Watts per meter squared. Power density in space. The reason why we call it the uniform plane wave is because if we plug in our expressions for E and H into this expression, we find that the power density is uniform. It doesn't matter where you go along the uniform plane wave. You always get a constant. In fact, I can show you E naught squared over 2 eta times k hat is the Poynting vector for a uniform plane wave. You take the amplitude of the E field, that's E naught, amplitude of the H field, which is E naught over eta, divide by 2, because we're taking the average, and the direction of transport of the power is, of course, the direction of propagation. That's common sense. And so there you have it. That's the average energy. In this case, for these numbers that I've given you, if you plug in our E and our intrinsic impedance, you find that this is going to be transporting 18.8 times 10 to the, let's see, we've got something that is the original expression. The E field was about 100 microvolts, and the H field we said was about 375 nanovolts. So let me get out my calculator. I don't want to skip this intermediate step here. I want to actually work the math. Turn my calculator this way so it's all scientific. So that's 375 nanoamps, that's 10 to the negative 9, times the original E field was 100 times the square root of 2. Times 100, and that was to the minus 6. I think that was microvolts. Divided by 2. It should be, I think it's negative 12 is what I got. And that's watts per meter squared. And so if I multiply that by 2, I get 2 meters squared, the size of the aperture. I collect all that power, and I get 37.5 picowatts. Wow, 37.5 picowatts. That's a tiny, tiny amount of power. And yet, it's a surprising enough power to do communications. That's not a bad number. And we've worked this problem from we started with mathematics. We ported as much as we could into the physical domain so that we could work with things like watts per meter squared, apertures, frequencies, that sort of thing. What we do next is to develop a framework where we can deal, instead of E's and H's, we deal strictly with powers. And this is where the concept of antenna gain comes in. So most of the time when you work an RF problem, you're not given the aperture of an antenna. You're given its gain. Now, it turns out those two things are related because, at least from a receiver point of view, an antenna is really like a cookie cutter in space. You have this plane wave that's uniform washing over the antenna. Why is it uniform? Because you're in the far field of an antenna, and all waves look roughly uniform from the far field of an antenna. It washes over there, and there's this effective aperture over which it gathers energy out of the plane wave. You can think of it as if you could see the plane wave. If the plane wave was at optical frequencies, this would be roughly the size of the shadow that was cast by the antenna because it's taking the energy out of the incident wave. In some instances, it's also reflecting it back, but that's a different story. And so, not surprising, especially for these larger antennas, a dish antenna, the physical aperture is going to be a pretty good estimate of its electronic aperture. There's some other inefficiencies that we're going to learn about that you have to take into consideration. But that's pretty much it. You got a big antenna. It's got an aperture. It gathers energy and power out of a plane wave according to that size. Other types of antennas, especially the electrically small ones, are the concept of a physical aperture tends to decouple from an electromagnetic aperture. You take like a dipole. A dipole is just a little thin piece of wire. It casts a shadow, so to speak, with fuzzy edges. That's not trivial. It'll actually absorb a lot of energy as it resonates at the frequency of excitation. However, its physical aperture is just a piece of wire. There's hardly any physical aperture. It's practically zero. So if we just try to extend that analogy to all antennas, it doesn't work particularly well, especially for the little stuff. But we'll get to that a little bit later, or when we cover some antenna theory.